A very warm welcome to all of my students in my YouTube channel as well as my Facebook page. Today I will discuss about the Brahmastra of statistical mechanics. Believe me, if you could adopt this technique, any kind of question which would come in competitive exams, NET, GATE, and it is related with statistical mechanics, you can answer it very easily. First you need to adopt the concepts. As we know that if you could know the partition function term for a system of particles, you can find out free energy, entropy, internal energy, chemical potential, lots of entities. But what is the main challenge, or what is the main thing we should understand? How to find out that partition function? At first, we must see what it looks like. What is the mathematical terminology or mathematical expression of partition function is? It is nothing but it is summation over gi into exponential minus beta ei. I am again telling, it is summation over gi into exponential minus beta ei. Here beta is actually 1 by kt, where k is the Boltzmann constant and T is the temperature. Gi is actually the degeneracy for a particular state who has got an energy of Ei. Gi is actually the degeneracy for a particular state which has got an energy Ei. If you could find this thing, you can find the partition function. And if you could find the partition function, you can find the free energy is nothing but minus KTLNZ. You can find the internal energy, you can find the entropy, everything. I am just giving you a small problem. I am discussing a small problem where you can find how to find this partition function very easily for classical particles which actually follow Maxwell-Boltzmann distribution, for the bosons and for the fermions. So let's see the problem, what it has been given. You can see that in the problem it has been provided that there are two particles, and these two particles are kept in 3 energy levels. They can be kept in 3 energy levels, and that are 0, E and 2E. 0, E and 2E. We have to find out the partition function for the system if there is one possibility, if the particles are indistinguishable and they are classical, the particles are distinguishable and following Maxwell-Boltzmann distribution, and if the particles are bosonic in nature, or if the particle is fermionic in nature. So in the first portion, we will try to solve for the classical system. We all know that in classical system or classical distinguishable or indistinguishable cases, it will follow the Maxwell distribution. And as far Maxwell distribution is concerned, we know that the partition function for two particles will be equal to Z1 into Z2, where Z1 is the partition function for the particle A and Z2 is the partition function for particle B. Remember, this technique can only be applicable for Maxwell-Boltzmann distribution. Okay, suppose if there are n number of particles, what would be the total number of partition function, or what will be the total partition function? It will be equal to Z1, Z2 dot Zn. Okay, so what is our aim here? We will take any of the particle out of A or B and try to find out that what kind of combinations we could get in different energy states. We know there will be no limitation of the particle to stay in a particular energy level. So let's see the diagram I have made here. So what are the possible configuration for this system? See, there are 3 types of energy levels you can find out in this case. It's 0, E and 2E. At first I have kept the particle A in energy level 0. In the second configuration I have kept the particle A in energy level E, and in the third combination I have kept the particle in energy level 2E. And I have also made a chart of having the total energy. Now we have already got the total energies in my chart. You can see the problem in your screen. So in this, now it's nothing left, just put it in the formula. It is nothing but gi into e to the power beta ei, because there is no degeneracy, so here gi will be just 1, and the partition function for particle A will be e to the power minus beta into 0 plus e to the power minus beta into e plus e to the power minus beta into 2e. It will be the partition function for particle A. Similarly, if you could try to find out partition function for particle B, it will be also be same with that. So the total partition function z is nothing but z1 into z2, and that will be 1 plus e to the power minus beta e plus e to the power minus beta 2e, that's whole square. That will be the case for classically distinguishable particle. But if they are indistinguishable in nature, if A and B are indistinguishable in nature, we have to put a 2 factorial in the denominator. Then the answer for the partition function for indistinguishable classical particles will be 1 plus exponential minus beta e plus exponential minus beta 2e whole square divided by 2 factorial. This will be the case for Maxwell-Boltzmann distribution. But if this two particle system is fermionic in nature or fermion in nature, what should we remember? We should remember that fermions cannot stay in a same energy state. Because they are Fermi principle, they cannot stay in a same energy state. So what will be the configuration? What will be the configuration or combination of states in this case? You can see it's clearly on the screen that I have shown the different combination possible for that, and also I have made a chart for that, what will be the total energy for every combinations. And it's natural, if you could find or if you could understand this chart, naturally the remaining portion is to find out the partition function, and that will be equal to exponential minus beta e plus exponential minus beta 3 and exponential minus beta 2e. That will be the partition function for this system if it is fermionic in nature. In the next video, I will discuss about if the system is bosonic in nature, what will be the combination or what will be the partition function for this system. So stay tuned with me. Thank you.